Let f be a function of two variables, x and y, such that it's given by the inverse tangent of x squared plus y squared divided by x plus y. We'll need to find out the value of partial derivative of f with respect to x and partial derivative of the function f with respect to y. So let's begin. So we will consider our function f. So let's begin with that. We have the inverse tangent of x squared plus y squared divided by x plus y. So let's label this as equation number 1. Now what we'll do, we'll take the partial derivative on both sides with respect to x. So here we have on the right hand side partial with respect to x of our function inverse tangent of x squared plus y squared divided by x plus y. Now we know that when we have a derivative of the inverse tangent function, so that's given by 1 over 1 plus x squared. So that means in our case, we have 1 divided by 1 plus. So here, the argument of the inverse tangent function will be considered as x. Then we have x squared plus y squared divided by x plus y whole squared. But then again, we'll have to multiply it to the partial derivative with respect to x of the argument, which is x squared plus y squared divided by x plus y. So here we use the chain rule. Solving this gives us x plus y whole squared, and in the denominator we have x plus y whole squared plus x squared plus y squared whole squared. So now we'll have to take the partial derivative of x squared plus y squared over x plus y using the quotient rule. So let's begin. So here we have in the denominator x plus y whole squared. Then in the numerator we'll have x plus y, starting with the denominator, multiplying it to partial derivative with respect to x of the numerator minus the numerator times partial with respect to x of the denominator. So let's further simplify the numerator. So here immediately x plus y whole squared will get cancelled out from both the numerator and the denominator. So we have 1 divided by x plus y whole squared plus x squared plus y squared whole squared. In the numerator now we have x plus y multiplied to, so we have to take the partial derivative of x squared plus y squared. Let's do that. So partial derivative with respect to x of x squared plus partial with respect to x of y squared minus x squared plus y squared multiplied to partial with respect to x of x plus partial with respect to x of y whole divided by 1. So here we have already cancelled it out. So that means we now have x plus y multiplied to, so partial derivative of x squared with respect to x will be 2x, and partial derivative of y squared with respect to x will be simply 0 because y will be treated as a constant whenever we are taking the partial derivative with respect to x, minus x squared plus y squared multiplied to partial derivative of x with respect to x will be 1 and partial of y with respect to x will be 0, whole thing divided by x plus y whole squared plus x squared plus y squared whole squared. So let's now simplify the numerator. So we have 2x multiplied to x plus y, so we get 2x squared plus 2xy minus x squared minus y squared, whole thing divided by x plus y whole squared plus x squared plus y squared whole squared. So therefore we now have partial of our function f with respect to x, so that will be given by x squared plus 2xy minus y squared divided by x plus y whole squared plus x squared plus y squared whole squared. Next, we'll try to find out the partial derivative of our function f with respect to y. Let's do that. Now from equation number 1, we again consider our original function f. So we'll take the partial on both sides with respect to y. So here we have partial with respect to y of tangent inverse of x squared plus y squared divided by x plus y. So the derivative of the inverse tangent function will be 1 divided by 1 plus x squared, where x is actually x squared plus y squared divided by x plus y whole squared. So this will get multiplied to partial with respect to y of x squared plus y squared divided by x plus y, obtained as a consequence of the chain rule. That means we now have x plus y whole squared divided by x plus y whole squared plus x squared plus y squared whole squared. But this will be multiplied now. Now we'll have to take the partial derivative by using the quotient rule. We have x plus y whole squared. In the numerator, we have x plus y multiplied to partial with respect to y of x squared plus y squared minus x squared plus y squared multiplied to partial with respect to y of x plus y. So here, the denominator and the numerator cancels out, and that leaves us with partial of f with respect to y, which will be equals to x plus y multiplied to partial of x squared with respect to y plus partial of y squared with respect to y minus x squared plus y squared multiplied to partial of x with respect to y plus partial of y with respect to y whole divided by x plus y whole squared plus x squared plus y squared whole square. That means we will further simplify the numerator to get x plus y multiplied to, so partial of x squared with respect to y will be 0 because x will be treated as a constant, plus partial of y squared with respect to y will be 2y minus x squared plus y squared multiplied to partial of x with respect to y, so that will be 0, x will be treated as a constant, plus partial of y with respect to y, simply 1, whole thing divided by x plus y whole squared plus x squared plus y squared whole squared. So let's multiply 2y to x plus y, so we're 2 times xy plus 2y squared minus x squared minus y squared divided by x plus y whole squared plus x squared plus y squared whole squared. Therefore, finally, we obtain the value of our partial derivative of a function f with respect to y, which will be equals to y squared plus 2xy minus x squared whole divided by x plus y whole squared plus x squared plus y squared whole squared.